next talk by Professor John Stankovic from the University of Virginia. And the topic is about the Internet of Healthcare Things. So a very promising application area for the Internet of Things. So John, please have the floor.
All right, thank you. Uh-oh. I forgot to include the sound, so that's why I'm going back and I have some more. Sorry about that.
Yeah, no problem, John. Take your time.
All right. So can everyone see my slides?
Yes.
Yes.
All right. So thank you for the invitation, and I'm going to discuss the Internet of Healthcare Things, work we're doing. And I just want to mention, though, that I'm the director of a link lab at the university, which focuses on cyber-physical systems research and the Internet of Things research. It's quite a large lab. We have 40 faculty and almost 200 graduate students. So before I get into my meat of my talk, I'd like to start with a question. So is the Internet of Healthcare Things really just hype, or is it the portend of a revolution in healthcare? And so we believe it will be a revolution, and partly because of what I have listed here on the slide. Smartwatches are becoming very common. They're more and more sold. They have more and more sensors on them, more apps that are running on healthcare issues. Smart skin is showing up, as this is a very interesting product. It's a wearable, if you could think of it that way. Smart textiles is another wearable. And then there's the opportunity to also build smart homes and have, in-situ systems. So combining all these, I believe, will indeed provide a basis for a revolution in healthcare based on the Internet of Healthcare Things. So the vision that we have, as many others working in this area have, is really a kind of a holistic vision. So, for example, if we have this elderly person and they may have these pills that they swallow that have cameras in them, and they can go around the body and look for problems. Pacemakers are in-body sensors and actuators. Then you could have on-body wearables like the smartwatch or pendants. Then we could also have the smartphone, which is running many different kinds of healthcare apps. I really like this ad I saw for a smartphone that said, let me back up. So when I go to the doctors, I'm sitting in the office and waiting, and finally they come out and say, you can see the doctor now. So with the smartphone, I saw an ad that says, your smartphone will see you now. And it's pretty interesting, I think. And so in other words, you don't really have to wait anymore. You can get a lot of information. You can also have devices on structures like sensors and actuators, maybe on a walker. So if a person starts to fall, the walker actually contradicts that. The person will be living in an environment, a smart environment, which will have lots of support for activities, monitoring activities of daily living, and so on. If they go out in the environment, there are smart cities and smart worlds that are based on IoT will maybe provide information about pollution and other issues that might affect a person's health. All of this is connecting to the internet with different kinds of websites, different online analytics, data mining to understand medical issues. The information is kind of collected from an individual as small data, I'll call it, because it's time for a specific person. But then there's the general population information coming in, and combining the two has tremendous potential. And in other words, this is really a kind of complete holistic view of trying to deal with healthcare for people. And what's really interesting, I think, is I would call the first generation was mostly just collecting information and then maybe presenting it to a doctor or presenting it to the patient. But now there's much more going on with actual actuations to encourage the adherence to different medical problems. So for my talk, I have three main themes. One is that, we're going to focus on what we're doing with wearables, and the idea is that these wearables are going to combine with cognitive assistance. So we don't want to make just dumb wearables collecting things. We want to make them smart. And to do that, we need a lot of machine learning and natural language processing. And within that context, one modality, speech, is really a powerful one. So we do a lot of work with Acoustics using machine learning to understand various things about a person, and the smartwatch can collect that speech, for example. So the first example I'm going to give is really combining these first two, and it is pretty high level. And then the next example I'll give of our work is based on Acoustics, which is a bit more technical. All right. So within the cognitive assistance, we're actually looking at at least three different projects. One is figuring out ways to make the smartwatch a cognitive assistant to help people with the COVID-19 problems, pandemic. And we also have built a system for cognitive assistance using some system we call MedRem, and I have a short video on that. And it's for working with the UVA Center of Telemedicine. And we also have a cognitive assistant for first responders, and we're working with North Garden Fire and Rescue, which is a local outfit, and Richmond, City of Richmond's ambulance service. And each of these kind of cognitive assistants requires different vocabularies and different kinds of solutions, it turns out. So let's look at the first one, and I just want to overview it and say the idea is that we can take a smartwatch and put lots of services on it, and we can combine these services, and a collection of them looks like a kind of a cognitive assistant. So the first thing we have is support for hand washing, and it's not just the fact that they hand wash or not, or they should hand wash for 20 seconds. So those are kind of very simple things to do, but we have a more complicated solution, which I'll show. Then we can also detect depression or loneliness through the watch. We can have voice-based conversations with the watch where the person can ask for different pandemic information. We can provide lots of reminders and alerts or advice to the people. We can collect various physiological parameters and then try to match those to different symptoms of the virus. Okay, so let's look at these a little bit more detail. So for hand washing, the World Health Organization has various guidelines, and they really indicate how to do hand washing correctly. So we were interested in identifying the quality of the hand wash to make sure that the virus is not there anymore. And the solution, which I won't go into, is based on a hybrid CNN RNN model for machine learning. And if you're interested, we have a paper which describes this in detail. It's been published. And so also with the hand washing, we send reminders to do hand washing often, and also if a person returns home, we can detect that with beacons, and we can tell them, remind them that since they just came in from outside, they need to do hand washing. And so the WHO guidelines for hand washing really is more complicated, and these up here are just whether you're using gels or water or kind of another soap from a dispenser. But what we do is these 6 in here are different patterns you're supposed to use to get all parts of your hand. And so our solution can detect that you're hand washing, but also can detect which of these you're doing. And if you don't do all of them, we can tell you, wait a minute, you did your hand washing, but you forgot to do this kind of step 6, right? And so that's why it takes a lot more complicated kind of machine learning solution to achieve that. For depression, we can detect the person's voice when they're talking to the watch. Remember, the watch has got this exchange that can occur. And so we have the microphone on the watch, we collect the voice, and we can basically identify if there's depression or not. And later in the talk, I will go into details about how to detect depression. And for here, I'll just say we put this as part of a feature on the smartwatch. And to solve this problem here, we basically use a bidirectional LSTM using multiple instance learning. And again, I'm not going to look at this. In fact, this kind of solving depression with the watch, the person lifts the watch towards their mouth, so they're very close to the watch. So the solution is based on this bidirectional LSTM. But we also have detection of depression in homes, and that's the one I'm going to describe in a few more minutes. And in addition to detecting the depression or loneliness from the voice, we can give recommendations and notifications and trying to encourage them, for example, to call their children or go out and do something, or try to maybe even make a psychologist aware of their problem and so on. The voice-based exchange includes ability for the person to do questions and answers with the smartwatch. And so we not only provide reminders. For example, a person comes back from having a stroke, and they go home and they take our smartwatch with them, and then the doctor gives them medications, they give them different kinds of potential exercises they need to do to recover from the stroke. And so there's a built-in reminder system that encourages the person to do these things. They may even give them advice or alerts that there's some problems. The person can ask questions. They can ask questions about the medications they need to take, or they can ask questions about the exercise. They can say, well, which exercise was that again, and why am I doing it? And so we have this it's a flavor of a cognitive assistant. They can also ask questions about the virus and the status. So they can say, for example, how many new cases of virus in Virginia today? How many deaths? How many in the States? How many in the world? And so we go out from the watch, we go out to the web, and we have websites where we collect that information and then present that back to the user verbally.
John, 10 minutes.
Okay. Psychological parameters, we can have an EKG, we can have temperature, we can add respiration and coughing to detect all symptoms of the virus, and we can kind of try to relate that back to that they may be getting sick. Let me give a brief demo, just give you some idea of how the watch, it's about 2 minutes, somehow idea of how the watch would work.
Welcome to the demo of MedRAM. So I'll receive a reminder. It's for checking ECG. So I tap on the reminder.
It's the time to do an ECG. Do you want to try it now?
Yeah, sure. Please tell me details.
Okay, press the crown to go to apps. Tap on the ECG app and follow the instructions.
Okay, so now I follow the instructions. I go to the ECG apps, and now I can do the ECG. Received a reminder for a pill.
It's time to take your nightly medications. Take all medications as directed by your physician.
Please tell me details.
Metformin and carvedilol.
Okay, thank you. Can you remind me after 1 minute?
Okay, remind you after 1 minute.
Okay, thank you.
You are welcome.
So this is the website for the doctors and the clinicians to view the patient data. It fetches the data from the cloud server with the data from the patient gets uploaded. So let's find the data for the patient 2000. So here we can see that the patient ID and the number of reminders provided, the number of reminders the patient responded, the response rate, and interaction between the patient and the system for each of the treatment. So by these, the doctors will be able to see what exercise or what medication or what treatment did the patient exactly follow day by day.
Okay, so I hope you get a little bit of a sense of how a cognitive assistant on a smartwatch might be used, and the video doesn't show all of the features, but it shows a few of them. So let me move to talking about acoustics, where we try to exploit speech to detect emotion. And so what I'm going to discuss here is this first one, distance emotion recognition. And we've also used it in a lot of other contexts here, which I won't go into. But if people are interested, we can talk to me, after the talk. Okay, so what the big difference between a lot of research that's been done on distance emotion was that it was done where you collected voice when you're close to the microphone, either holding a microphone or there's a fixed distance to the microphone. But we're interested in when there's a distance from the microphone, because that's what really happens in a home. So let's say we have a smart home that's going to be detecting various issues with respect to health, including emotion. And so there might be microphones in different places. Here's one on a table, and a person may be at different distances from that microphone. That affects the quality of the sound. There could be two people talking, multiple people, and so on. And so we need to solve the problem with worrying about distance, and that includes problems with de-amplification and reverberation and so on, and multiple speakers and overlap speakers. And so our solution has three parts to it. The first is dealing with distance agnostic features. The second is feature modeling, where we have a new vector model called emo2vec, and then we take these features into a classifier down here, which is an LSTM. So let me quickly go through each of those. The first is, how do we select the features? And so in the past, we saw that most research that works well when you are next to the microphone considered 231 low-level descriptors as features. And this table here has those features in it. The table has something like 77 features, but then you also use the delta and the delta to get to the 231. Now, what we did is said, well, out of these features, a lot of them have to do with volume or energy, so they're going to be not very helpful when you're at different distances from the microphone. And so we ended up doing a lot of experiments and finding 48 low-level descriptor features that are distance agnostic. So we basically just use those features, not the 231. And when we create what's called audio words, and let me give you an example. So first of all, I said we have 48 features, so that's 48 dimensions. But this example I'm going to give is only 2 dimensions. So suppose we have this sound from the voice, and within this little window here, which is 25 milliseconds, we extract features from that. And in this case, we only have 2 features, so I can plot it here and show you. And so when I look at this window and I plot these features, it might be this word here, this value. So it has an X and Y value. We plot it here. And then the next one, the next window has another feature. Maybe it's over here, and so on. Now, in reality, we have 48 features, so it's a 48-dimensional space. But after we do this training on many, many different voices and so on, we end up with clusters of values, and we take the centroid of those values, and they become what's called an audio word. It's not really a word in English or anything like that. It's just the value of those features, but it's called an audio word. And then we take the centroid, and if, for example, once it's all trained, there's a new point, say there's a new point that we are finding in a particular person's voice, we map it to the closest centroid. Right. Another new word maybe gets mapped. So even though there are differences in two or more, kind of set of feature values, they might get combined into the same, what's called a word. All right. And it turns out, the size of that, how many clusters you need, is called a code book size. And we tested everything from 500 to 2,500 sizes, and using k-means clustering to do that. And it turned out that if we looking for happy, sad, angry, and neutral as different kinds of emotions, each of those required a different code book size. So there wasn't one code book size for all across all of them. We also then take these words and we create a vector representation called emo2vec. If people are familiar with word2vec, it's very similar to that, except that it focuses on emotions and not just general words. And so here is an example that, let's say, a particular word in that previous diagram, we just labeled it A here for purposes of explanation. And then we have these other words are the context of this. So these other P, Q, R, S, T, and so on are words that are surrounding this word. And then if I look at B has got the same context practically. If we got, P, Q, R, S, T, U, and here we got P, Q, R, S, T, U. So that these two words, A and B, are appearing in the same context. So we take those and we assign them vectors that are close to each other, assuming they're in the same emotion. So both of these were in, when we're training, both of these are in happy, so that the vectors representing A and B are modified to be close together. However, here we have A and now we have C, and C is really part of not happy. And even though it has the same context, P, Q, R, S, T, U, P, Q, R, S, T, U, we basically take the vector for C and make it separated from the vector for A. And this vector representation is called emo2vec. Right. Then what the basic overall structure is to take these, after all the training is done, we take a sample of voice that's shown up here, and then we take this window and we take out the robust LLD features, low-level descriptor, it's 48 features. Then we convert those into their vectors, and those vectors go into the LSTM classifier. And then we just process across the speech, and at the end we decide if it's, we usually take about 5 seconds to decide what the emotion is, all right? So that's just high level. We did a lot of evaluation on this. We used 2 literature data sets. We used our own family discussion experiments where we brought families into a lab and we had 28 people coming in and talking and collecting data. We also compared to 4 baselines from the literature, and this solution is approximately 16% better than the best baselines. Just quickly, I'm not going to show all the results, but just to give a high-level view. So in order to detect angry, happy, and sad at distance, here, this shows the accuracy, and this is the recall. And you see it's around 90%. So we're collecting about, actually, to detect angry, happy, or sad, we're getting about a 90% accuracy by using our approach. We also just show one more graph where, what if we used all 231 features instead of the 48 that we just felt were distance agnostic? So the orange line here shows the accuracy when we use all of the features, and then the blue line shows the accuracy when we use just the distance agnostic features. And it's roughly about a 10% gain by getting rid of unhelpful features, basically. All right. Just quickly, I mean, we also have many other projects, and the new one is with dealing with Alzheimer's patients where the caregiver is getting stress, so we can detect the stress and emotions from voice from the caregiver, and then we're trying to, using reinforcement learning, giving recommendations to the caregiver to improve their stress and reduce their stress. We also have a project on family eating dynamics for obese families. And the reason I'm just showing these is because the idea that almost anything in healthcare can be developed into kind of apps and using machine learning to help support projects in those areas. All right, so let me just conclude. What I try to show is that we're trying to do work on smart and connected health based on wearables largely, and trying to not just collect the information, but apply it in a way that it's producing a cognitive assistant for people. And all of these products and so on are really connected to the internet. So, that there's a lot of ability to apply this to almost any morbidity, or very many people have comorbidities as well. Okay, so I will just finish there.
Okay, thank you very much. There is already one question from the audience. So the question is, in the case of hand washing, can you tell more about the reactions of the users when they are told that they did not perform the actions correctly? And the second part, in your opinion, how important is the user acceptance and the adoption of such technologies?
All right, so two very good questions. So the first one is, we have not deployed the system, the hand washing, as I presented it, with real COVID-19 patients and so on. So we really don't have a complete answer to that. However, we have done an earlier system with hand washing for doctors in the pediatrics intensive care unit. And there we were providing feedback to them saying that as they go between patients, if they didn't wash their hands, we would remind them, we would buzz the watch. And their feedback was very positive in that, we promised them we weren't reporting them, or anything like that. So they didn't feel like they were under scrutiny, and they felt that, oh, you know what, this is helpful because sometimes I forget to wash and I don't want to cause problems of possible infection. And so having that buzz is really helpful. At the same time, we found nurses wearing it, they didn't accept it as well. They felt that we were going to be monitoring them and we might report them. And their initial reaction was, yeah, but we always wash our hands, so we don't need this. Right. And but that's not true. There's a lot of information out there that shows that people do forget. And so I think acceptance is a critical issue, of course. And I think acceptance, in my view, varies as a function of how serious their problems are and how well they feel that this can help them. If they don't feel it helps them, then they're not going to do it.
Okay, thank you. There are some more questions. So one is, what approaches and algorithms were you using to define the context of how the words are used in the sentences for the emotion analysis tool? Do you consider other aspects of the speech analysis like irony, etc.?
All right, so no, we don't consider irony or anything like that. But the other thing is, we're not using text at all. We're not using the words. So when we say audio words, it's not English words. It's simply let's say I have an audio word that has just two features, X and Y. So those two features might be the pitch and the kind of prosody metrics, like the maximum value or something like that. So that values for those two things is the word, not the word John or something like that. And so it certainly is interesting to combine, if we convert people's speech to text and then we analyze the text as well. But that's also a possible privacy problem. So we try to stay away from that, and we indicate to people that we're only using the properties of the speech, not the content of the speech.
Another question. Well, first the comment says, very interesting talk, thank you. And the question is, how did you reduce 230 LLD to 40 odd LLDs? Well,
we did it by experiments. So, we essentially use data sets as well as our own experiments to kind of identify which features were making a difference in the success rate of detecting the emotion.
Okay,
and it turned out that most of the features we ended up eliminating were basically features that related to energy or volume. And that's somewhat understandable because if you're far away from the microphone or close to the microphone, the volume is going to change. And like for example, to detect sad, if I talk in a microphone and people normally when they're sad, they have low volume. So when you're right next to the microphone, you assume that, then sad is important to have volume. But if I'm far away, the volume may be the same and it have nothing to do with sad. And there's a technique called feature selection used in machine learning where you basically are stepping through all the features and identifying which ones are effective in doing classification.
Okay, thank you. There is one more question. The question says, what about validation of these apps and devices by health authorities? Perhaps I could also complement this with one remark, that is, in Europe, we tend to separate health care from normal elderly care and assistance. So in fact, it's kind of two separate communities. So I guess this question has to do with this more strict regulations for the health part. So how do you see it?
Yeah, so again, that's another very good question. And in the States, there's a agency that approves healthcare products or apps and so on, but they've been pretty lenient about it as long as the apps and are not making medical decisions. And they don't want to hold up progress by saying, okay, everything you do, you have to go through the FDA and get approvals before it gets used. So, for example, we have no FDA approval to put smartwatches on the doctors in the hospital. We have an IRB, but we don't have anything else. And then the doctors are just saying, okay, use it, and they find it, say, helpful, and then would they recommend its use? We're trying to make it into more general where we could use it in many hospitals or make the app available, but it also doesn't supplant the doctor. I mean, the doctor's still there and they can still make their decisions and so on. But I think certain medical, if you have an image analysis that detects cancer and you're trying to take a picture with a smartphone and then the image analysis is going to tell you have cancer or not, well, that probably needs FDA approval. Or what people do now is they say that's just a precursor that then warns the doctor there's some problem, and then they go through their normal gold standard tests.